So good morning, everybody. Nigel Forrester, Director of Strategy from Concurrent Technologies. Really pleased to be here in person to present to you about Dreams to Reality. So in preparation for this event, I looked at, where were we the last time we had Embedded Tech Trends? I think it was 2019. And as a result of that, and I can't remember if it was immediately after the event or during the event, I had an illuminating conversation with Dr. Lipkin, who I'm sure many of you here will know, who encouraged me, perhaps that's a bit mild, probably told me never to darken his door unless we were to deliver on the promises that him and his colleagues needed to develop some of the applications for the types of application that him and his colleagues need to do with capabilities like 100 gig Ethernet. So this slide here is from the current SOSA open group website, but effectively it captures the essence of what we're trying to do here is to come together as an ecosystem to develop the technologies, be it at the connector level or the board level or the system level, to deliver the types of systems into the marketplace that are needed. And now that was a big challenge. And if I'm honest, at the time, we didn't have 100 gig Ethernet capable cards. We had 10 40 gig capable cards. We didn't have PCIe Gen 4 or 5. We had PCIe Gen 3. So there's a lot of technical challenges that we had to come to. However, I'm going to split my presentation into two halves today, a bit more of a softer approach, so some of the challenges and how we've evolved to deal with those, and I'm sure many of the other companies here can empathize with that, and also a little bit about a technology that we haven't talked about much at Embedded Tech Trends that I think might be interesting. So first of all, let me introduce you to a couple of my colleagues. So this is on the right here is Andy. So he's now our longest serving employee. I think he's been with the company about 35 years after a couple of other colleagues have retired. And then there's Liam down here, who's also been with us a long time. So shortly after Embedded Tech Trends last time, we basically told Andy, who is our head of CAD, who'd worked in the office for 33 odd years, to go home, along with everybody else in our company, except for the guys who worked in our production team or our labs, like Liam. So that was a significant change in behavior that everybody had to deal with. How do you deliver the types of capabilities that are challenging us as a company to do all of the things that we need to do between our marketing teams, engineering, our software teams, our production teams, to come together to do that when we're all remote? That was a real challenge. So what we've worked on really hard is now, once we're past the pandemic stage, how do we invigorate those teams? How do we bring on new employees, especially younger employees, and how do we bring them back together as a team? So we've done a lot of things to enable that, including completely revamping our offices. So this is from one of our two offices where we've invested heavily in trying to make a space that people want to come and work in, because what we really want to try and do is to collaborate better. And whilst you can do that over a Zoom or a Teams call, it's much harder. And so we've worked really hard as a company to do that. We've also, I'm pleased to say, a little bit ahead of the Embedded Tech Trends, is we actually had an all-company event in May of last year, where we tried to bring everybody in the company together to try and give them an idea of what we needed them to do to deliver on this sort of technology, how we were going to come together, and how we were going to invigorate them and bring on some of those new people. And we've also worked very hard in terms of mental health and well-being. So think about those people who were asked, unlike us, who were quite used to socializing, maybe in a sales, marketing, business development type environment. We're very good at picking up the phone and talking to people. Many of those engineers are not. They have different characteristics, different mindsets. It's been very difficult for them, many of them, to actually keep invigorated, get up in the morning, do what we need them to do. And so we work really hard in terms of developing those mental health and well-being capabilities. So the image on the right there is a recent walking meeting we had where everybody was encouraged to go out, take a break, get some fresh air and things. So with all that said, we had another problem. So everybody here will have heard about the component crisis shortage, where we've gone from a situation where we could pretty much source most of the components in a very short lead time to a situation last year where we didn't know, in all honesty, when we were going to get some of the components because they were on allocation. And if they weren't on allocation, the lead times just continually went out. And very often, we were at the stage where we were building a product. Tomorrow, the supplier rings up and says, oh, by the way, we're not shipping you your components that you need to do that. So hopefully, we're seeing some green shoots that is improving in 2023. We've worked really hard with a lot of our component suppliers, the best example being Intel, where they've always managed to deliver us the components that we need on the date we need to build our boards. Unfortunately, most of our products have 1,000 type components from lots of different companies, and we can't ship boards with 99.9% of the components. That last, whatever it is, makes a big difference. So there's a lot of effort that's been required to do that as well, and still sort of maintain that cadence of delivering things. So on top of that, I talked a little bit at the start about those technology challenges, and there's been some really good segues here today from some of the other presenters about what it takes to get to 100 gig Ethernet or PCIe Gen 5, and some of the other things that we need to do. And as a company, we've obviously been on a learning curve to get to that level, and we've had to upskill pretty much everybody in the company to make sure that the products not only are designed, but are tested, and we can validate those to provide them to the community. And I think we've done a good job. So the image on the bottom of the slide here is actually a simulation from one of our 100 gig processor boards. If I remember rightly, this is from in a 6-slot backplane between slots 1 and slot 6, and the eye diagrams and the other information there gives us the ability to have claimed before we started the design that it was a good design. Obviously now we've got to the stage of actually proving that in real life. So anybody who's got children here will know, famous words as soon as you get in a car is, are we there yet? Well, that's obviously for the audience to decide, I would say. However, I think everybody in this room can sort of give themselves, a pat on the back, really. We've come along a huge way. In that time, with all of these challenges, there's been a massive change in the ecosystem from the component side, chassis, backplanes, payloads, switches, and timing, which is what I'm going to talk about a little bit. So good shout out. I think one of the great examples as to are we really there yet? Our colleagues from Elma, Ken gave a couple of examples of real life demos that we've done together with ourselves, Elma, and ASO Rugged to demonstrate that we are at the stage we need to be at and we can deliver those sort of payloads. And there's many other examples now as the ecosystem starts to mature to do that. So the last point on this slide is the timing, and that's what I want to talk a little bit more about. So why do we need timing? Why is that important? Okay, so if you think back to the very first slide I showed with the applications that SOSA are trying to achieve, I think they're sort of listed on the right-hand side of the slide here. All of these applications need accurate and consistent timing. And there's been a lot of work over the years on the Vita specifications derived out of the advice from the SOSA community as to what we need to do to improve and make sure that those solutions that we can provide do provide that sort of accurate timing. So this is a screen grab of the profile for one of the timing slots. And in effect, what the timing slot does, and you'll see in most of the backplanes out there, they have timing slots. They provide radial clock signals to all of the other payloads. In this case, this slot profile has 11 payloads that it can accommodate, and it also has a cutout in the P2 position for an aperture there for optical or coax connections. So the sort of concept here, so it's a very simple diagram, is that the board in slot 1 there, which I've labeled PNT. PNT is position, navigation, and timing. We'll talk a little bit more about that in a minute. But the timing board, what it does is it can take input and it can provide outputs in that Vita67 aperture, and it distributes those radial clock signals across the backplane to each of the cards in that chassis system, except typically a switch card does not need a radial clock, but if you've got FPGAs or other cards that need accurate timing, you need to distribute those. And the timing card is really controlled across the control plane. So effectively what you do is you send a command to set it up, and then it sends data to you across the control plane. It's not so bandwidth limited, so it doesn't typically on the backplanes available today, it doesn't have a data plane connection. And as you can see on the top left-hand side of the chart, you can also have both incoming and outcoming timing signals if you want to synchronize other devices. So if I step forward a bit, this is a bit more of a representation in how that works in reality, is that you may need to make that timing absolute. And the easiest way of doing that is by having a GNSS input. So GNSS is the Global Navigation Satellite System. The thing which everybody recognizes is GPS, is one of the satellite constellations, the US satellite constellation. So that satellite constellation basically sends you absolute timing information. And that information is then used to discipline an onboard chip-scale atomic clock, and that chip-scale atomic clock then is used to distribute the timing across the radial signals, which in this diagram are either blue or red, to the other payload cards. And there are typically 2 timing signals in this system. The blue line is representing what's called the aux clock. That is a 1 pulse per second signal. The red is the ref clock signal, and that's programmable typically between 10 to 100 megahertz, and that's programmable on a per slot basis. And then, of course, if you've got a switch in your system, that information can be relayed to other boxes in either the vehicle or to other things in the near or short term accordingly. So the diagram here represents really what we're doing on typically a land vehicle. So there are other inputs into that that may be or may not be used, and there are also outputs. So what happens if the GNSS signal goes away? So we'll come to why it might go away in a minute, but what happens then is that the chip-scale atomic clock, which is designed to be as accurate as possible, effectively then generates the timing signals, and it carries on at a great, as accurate as it possibly can. So to give you an idea, over 24 hours and over a temperature variation, you typically see something like about 2 microsecond variation in the timing signals based on those chip-scale atomic clocks. A very, very accurate timing device. However, not as accurate as when you have GNSS disciplining it. So the other thing that you can do with these timing cards is that you can then use the timing source as a grandmaster for your other things in your system. So the timing card sends out IEEE 1588 precision timing protocol packets out to the switch or to other devices in the system, and they can then relay that onto other devices in the near vehicle or whatever else you're deploying this in. But there's many other examples. I mean, I think most of those applications that SOSA is aligned to, they all require, if they're going to operate successfully and they have signal processing devices in there, they have to be accurately synchronized, because what you do is you split up the various phases of the processing between the different processing resources. And unless you can split them up and combine them back again in incredible accuracy, because you might have, say, maybe a 5 microsecond window or something to do the processing and reassemble the packet, then it doesn't work. Okay? So I want to talk, just to finish off really, talk a little bit about the extension to that timing card, because the devices that are available on the ecosystem are assured position, navigation, and timing. So timing is perhaps the most fundamental part, but it's not all of the parts, because a lot of the types of applications not only need accurate timing, but they need to know where you are, and they also need to know information about the navigation so that you can get to where you're going to. Now, if you've got GNSS capability, that's easy, because that's also part of the packet that you get from the GNSS network, and there's lots of examples here about the other networks, and there's also lots of schemes that can make that much more accurate, these satellite-based augmentation systems being a good example, but there's other things that you can add in to make that more accurate. However, what happens when that GNSS signal goes away? So easy example is if you drive through a tunnel, you don't get GNSS signal. However, tunnels are usually relatively short and quite often very straight, relatively easy to deal with. But there's lots of other examples as to why your GNSS signal goes away. Some of them are unintended. There might be people who are broadcasting on the wrong frequency quite close to you. It takes very low power. These GNSS devices are very low power. It's very easy to intentionally interfere with GNSS signals. So if you don't believe this, quick Google will show you what's happening at the moment in Europe around the Ukraine area, where there's a huge amount of GNSS interference to deliberately obfuscate people's navigation information. And even worse is when you're spoofed. So if your GNSS signal completely goes away, it's very obvious. Something's happened to stop that signal. It's often not so obvious if somebody moves you a few meters or 100 meters or a kilometer from where you actually are, because then you really are in no man's land. So in terms of actionable intelligence for the warfighter, it's imperative that we can provide them with the best possible information as to where they actually are that is independent of those GNSS signals. And that's a core function of the PNT cards that are available in the ecosystem today, that they detect when they are being spoofed, and they have a subsystem based on a Kalman filtering technique that actually tries to interpret the other inputs that they have to make sure that that position and navigation information stays as correct as possible, and when the GNSS signals come back, that they actually co-merge as to where they actually are in practice. Okay, so hopefully I've given you something interesting to think about there. That's a little bit different from the other presentations. I'd like to thank you very much for your time, and are there any other questions?